Okay, so we're going to think about circular motion and how we define a position vector. So if you imagine we have some xy plane and that a particle's motion, if you imagine we're looking down at the ground and a particle's motion is given by a circular path. So it will look something like this if that were a perfect circle. And that's the path that the particle travels at different moments in time. So let's say it starts here. So that point is the point of the particle, the position of the particle when t is 0. And then as time goes on, it moves around its path. So we can think of these sort of dots as the particle's position as time increases. And if we want to define the particle's position vector, well, we can think about the components in the x direction and the components in the y direction. So this position vector r is going to have an x component and a y component. Well, at some time t, that will change, so it will be a function of t. So if we just think about this point here at some time, well, it has an x component, which I can think of along the x axis, and it has a y component there. And if we want to define this, well, the particle has, in its motion, in its circular motion, that circle has some radius. Let's just call that r, not the position vector r, but just a scalar representing the radius of its circular motion. And it's turned through some angle in that time. So let's just call that theta. So we can define using trigonometry, that's a right angle triangle. If we think about this x component of the position vector, well, that's just going to be r cos of theta. And if we think about the y component, that's just going to be r sine of theta by basic trigonometry. However, we want it as a function of time. Well, the thing that's changing with time is that angle theta. The particle is turning through that angle theta. So let's just say that theta is some constant multiple of time. So omega t, I'm using omega, that's typically what we use for angular velocity. It's just the speed at which the particle is rotating through an angle. That doesn't really matter. We're just saying that it turns through an angle theta in some amount of time, some constant multiple of time. So let's just say for now this is some constant angular velocity. Okay, and now we can very simply substitute that into our x component. So this will become r cos omega t, and this will become r sine omega t. So back at the top in our position vector, I can substitute those in, r cos omega t and r sine omega t. So when we see this type of position vector with a very important that for circular motion, our radius r is constant. So we have a constant radius of motion. Okay, so now I'd like to look at a slightly different example. This time we have a particle's displacement vector at time t, and it's given by maybe a similar looking function. We've still got this cos of some function of t defining our x and sine of t defining our y. We have no omega, it's effectively 1. But this time the radius, so where we previously had the radius for circular motion, that is a function of t, so that is now no longer constant, so we'll see what changes. So initially I just want to be able to plot the particle's path, so its position at a few moments in time on the grid below. So I'm just going to substitute in various values of t into this equation. So let's say when t is equal to 0, if I substitute t is 0 into both the x component and the y component, in the x I will get 5, in the y 0. We're working with angles, cos, trigonometric functions, so let's pick t of pi over 2, we're working in radians. That's going to give me a position vector of 0, 3.65. Now I can look at when t is pi, that gives me a displacement vector of minus 2.670. We can look at when t is 3 pi over 2. That will give me a displacement vector of 0, minus 1.95. And finally, let's look at when t is 2 pi. That will give me a position vector of 1.42 and 0. Okay, so now I can plot those points as its position vector through time on the grid below. So when t is 0, we're at 5, 0. When t is at pi over 2, we're somewhere here. This is when t is 0, so that's effectively the start of its path. When t is pi, we're at minus 2.67, somewhere here, minus 1.95, and 1.420. So you can sort of imagine the path that the particle is taking. If I just directly connect these points up, obviously it won't be moving in straight lines, but you can hopefully see that it's spiraling. And maybe if I wanted to draw sort of a smooth curve representing this particle's motion, which would be the case at multiple values of t, so maybe there'd be another here, here. These are all these dots are the different positions of the particle at time t, and we can see that it goes through its spiraling path. So why is that? So it's spiraling. Well, we saw that the cos t and the sin t part, so cos t and the sin t, kind of define the circular motion, the rotating, and I'll put circular in bracket in inverted commas. We know it's not circular, but the radius is not constant of that circular path, because the radius is defined by well, this is our 5e to the minus 0.2 t, so the radius of its path. Well, let's think about what happens to that radius as time goes on. So we could say as time t gets bigger or tends to infinity, well, 5e to the minus 0.2 t is going to get very big. That means that 0.2 t gets big. This becomes a very big negative number, and e to some very big negative number is a very small number. It gets smaller and smaller and smaller, and it tends to 0. Okay, and that's why we get this spiraling path. Let's pop up here. It goes in towards the origin, 0, 0, because the radius is getting smaller and smaller. Now that we have our position vector defined up here for this spiraling motion, I can use it in the same way I would for any other type of position vector, which is a function of time. I can use it to find the velocity. So if I'm now want to find the velocity, I can use the derivative of the displacement or position vector with respect to time. You've got a function here that is a composite function, e to the power of some function of t. You'll need to use the chain rule. And there is also two functions multiplied together in each component. So you'll need to use the product rule as well. But if you're comfortable with that, you're just differentiating the x component and the y component separately, and you will get minus e to the minus 0.2t cos of t minus 5e to the minus 0.2t sine of t minus e to the minus 0.2t sine t plus 5e to the minus 0.2t cos of t. Okay, it's not particularly nice, and you could factor out e to the minus 0.2t, but now you have a function of the velocity or a vector for the velocity as a function of time, and you can use that in the usual way. You can find the velocity at a specific time, you can find the magnitude of the velocity at that time, you can find the direction.